Hey guys, welcome to week 11. We're almost there, 4 weeks left to go. So here we go, macroeconomics. We're finishing off our environment unit. We're just hitting it for a moment, getting some basic facts down on economics and the environment. And then next week, we're going to be moving into our COVID-19 unit, looking at how economics and pandemics work together. So that's going to be kind of cool, jumping in and taking a look at something that we're living right through at this moment. So in the meantime, let's go take a look at what's going on with our environment unit. We're going to be finishing off 20.2 and 20.3. So those are the last two parts that we're going to be doing with our environment unit. It's just enough to give us a taste of how do we look at things economically and environmentally, and ways that we can measure them, interact with them, and create policy and impact. Okay, so let's go take a dig in. I'm going to go to our core book. Okay, if we look at our assignment, I'll just go there real quick. What we need to do is read our core book 20.2, 20.3, and then do our workbook pages 6 to 8. So let's go take a look at that. So 20.2 is looking at climate change. Okay. So here what we have is 5 features that climate change share with other environmental problems, right? If climate change was easy to solve, we would have solved it already. It's pretty complex and it's tied in with other things that are currently happening. So, and this ties right in with our workbook. If we look at our question 20.2, what are the 5 features that climate change shares with other environmental problems? Okay, and why do these make climate change difficult to manage, right? How come we haven't solved this already if we know so much about it? So if I go back to my core book, I find out that stabilizing yearly emissions is not sufficient, right? Climate is affected by the total amount of greenhouse gases. Remember when we looked at the bathtub model, we saw even though we stopped creating more carbon, for example, we stopped that faucet from pouring more water into the bathtub was still overly full. Okay, and we didn't, well, if we turned off the faucet, then everything would go down, right? So if we stop producing carbon, then carbon's going to get reduced because it does have, a little bit of elimination in the environment, right? By plants absorbing it and soils absorbing it. So carbon does get absorbed, but it just doesn't get absorbed as fast as we produce it. So if we produce it slower, okay, we're still going to be maintaining those high levels that we currently have. What we have to do is produce not only slower, but less, right? And that's where the stabilizing emissions is not sufficient, right? Just saying, okay, starting now, no more. That's not enough, right? We have to do even more than that because we have to get the water down the drain. Okay, irreversibly of climate change, right? It's really hard to take back what's currently happened, right? And these things happen slowly. So even if we were to shut off that faucet on the bathtub today and stop all carbon altogether, there are still systems that have been impacted and storms and warmed oceans and all these things that take time to get back to where they once were. Okay, so everything is interrelated in many different ways. And a lot of times you can't just go back. All right, so you have that irreversibility. We have worst case scenarios, which we really don't know what they're going to be, right? People have been saying pandemics are coming forever. And, but no one really knows, well, when, right? And now we've gotten the pandemic, how bad is that going to be? We don't really know, right? And it's just like that with environmental things as well. It's hard to predict and it's hard to know. It's easy to look back and say, well, this is what happened. But at the time, it's difficult. And a lot of businesses and companies don't want to deal with a worst case scenario because it's expensive and it's difficult. And a lot of times it's felt like it's not necessary. Then we have a global problem requiring international cooperation, right? What we find is a lot of our countries in the global south, which have minimal economic production, minimal industrialization, they're the ones that are suffering the most from the climate change as it's affecting more environments around the equator, right? So environments in the southern hemisphere, like Africa and South America, and also countries that have less of an established economy, where they have less government reserves or money to be able to help mitigate or make changes or infrastructure improvements, to deal with climate change. So that's how it needs international cooperation. What the big producers, the industrial nations do, affect the smaller nations and affects each other, right? So China can cut down all their carbon emissions, but if the US doesn't, it still affects the whole world. Okay, and then we have conflicts of interest, right? To cut down carbon emissions, that means you're changing the way you're doing your production. And production is what drives the economy. So who's going to go first? How much is it going to cost? What's the incentive? Okay, those are all the conflicts of interest. Okay, so we're going to go put those in our book, talk about them. Why does it make it difficult, especially, conflict of interest when you're looking at the free market, and the invisible hand. There isn't much incentive for a business to become green, unless there's a customer demand or, there's some other force that's making them want to do that. But if you're just looking at typical supply and demand, building product, making sales, there isn't a place there for the environment. Okay. Number two, we have how are the changes in CO2 levels and temperature deviations below. Okay, and I've been writing in my book, so my pages might be different. How are they similar to that of the same time period on the hockey stick curve that we studied in Unit 1? Okay, so we're starting to see that same model again, right? That is 1750, so that long drawn out, and then suddenly, 1900, 1875, boom, things start going up. Okay, and here what we're measuring is the amount of CO2 in the atmosphere, parts per million, and we're looking at deviations, right, from the temperature average. So how much, here's our temperature average right here is 0. Okay, so how much below and how much above that temperature average we are. And we saw that, in the 1700s, we actually were, and this is just 1/4 of a degree, okay? So this is a really blown up model of a very small amount of space, okay? But in the 1700s, we're actually running a little cool, okay? And we actually had what they call a mini ice age, right? It was a period of cooling that happened even earlier than that in the 1600s. So we see ourselves starting to recover from that, right? And then boom, we have this industrial revolution, right? It happens in the late 1800s. And it's cool, and now it's warm, and here's our midpoint at 0. And we see our first spike was in the 30s, right? And then it goes down, and now we're back at normal, okay? We're at normal warmth. But then since 1975, we've just been climbing. And ironically, that's where the CO2 is climbing as well, right? So that's what we're looking at there. My question here is, what is another impact that rising CO2 levels have on the environment other than temperature? Okay, so let's go take a look at what the book has to say. We're going to jump back to our book. All right, here's the model that we just looked at. Okay, and here they're explaining the different activities that went and helped to create the increase in CO2, the fossil fuels that are being burnt, how much fossil fuels and carbon are being emitted. And then we have our model that we know so well, our bathtub model, right? And in this case, what's coming out is the CO2 emissions. What's in our tub is the amount of CO2 in the atmosphere. We have this natural decay that I talked about being absorbed by trees, right? They breathe in CO2, they breathe out oxygen. So when trees breathe in CO2, they're filtering CO2 out of the atmosphere, and then they're storing it in its wood, right? It's storing it in its tree. It's using that to build more tree out of. So that's why when you burn wood, you're actually releasing that CO2 back into the atmosphere again. But anyway, so trees take CO2 out, the earth absorbs CO2, grasses absorb CO2, even the ocean. So we have this idea of natural of absorption down here, And then we also have this idea of natural decay, where CO2 will just break up naturally, but slowly. Okay, and what we have emitting is much more, right, than what's being absorbed or being decayed. All right. And here we're talking about what are the things that are making this happen. Okay, kind of what I just introduced to you. And you can take a look at the podcast. There's a nice little podcast here. I didn't make it part of our assignment, but it's interesting to listen to. And so it's right here, Martin Weissman. Okay, and let's see. And the next thing that we're looking at is the relationship between temperature increases and CO2, and also looking at the amount of CO2 that would be emitted if. Okay, so this is the thing, like right now we have these CO2 levels. For example, now we're doing the tar sands, we're doing a lot of oil and natural gas. We have the fracking where we're getting natural gas. So there's more stuff, right? Even though we talk about peak oil and the fact that it's a non-renewable resource, there's still quite a lot of resources. And that's what this chart's looking at right here, is how much CO2 would be emitted if we burnt all of the fossil fuels that can be economically extracted at a current price point, okay? And we burn all the fossil fuels in the Earth's crust, the resources, okay? And that was like what we had looked at with the last unit, was the idea of resources versus reserves, right? We might have a lot of natural resources, okay, but we don't use them all, right? Some of them are not easy to access, okay? So when we're looking at this chart, we're looking at that same thing. So the reserves are what we can kind of get out of the earth right now, okay? So there's a bunch of coal, pretty easy to get. We have our oil, and there's some gas, okay? And now this is looking at how much the temperature will increase depending on how many of these reserves we're going to be digging out of the ground. Okay, so that's why one of the actions for helping to fight climate change is to keep it in the ground, right? Don't make those reserves get used, right? If they stay in the ground, the carbon that's locked into those reserves stay in the ground as well. So far, so good? All right, so here we have, even if we're using the reserves that we currently have access to and know about, we're seeing this rise in temperature. Okay, what we have here are the resources. So there's a ton of coal in the earth that we're not using as reserves. Okay, it's not economically feasible to extract this, right? It would just be way too expensive, really, really difficult, but it's there. Okay, we thought with the tar sands that those wouldn't be economically feasible to extract, okay, but we're extracting it. We thought with the fracking, the natural gas would not be economic to extract, but we're extracting it. So as we're pulling more of these resources out and turning them into reserves, we're also going to be increasing that temperature, right? So what this is looking at, though, is just valuing those reserves, those resources. So if they just stayed resources still sitting in the ground, if they were taken out and burnt, this is the amount of CO2 that would be getting emitted, okay? So huge, all right? And there's a lot of oil there too, and gas, okay? So that's what we're looking at, right? We have the potential to do even more damage than we're currently doing right now. Cool, especially as we have new technologies that might make these resources easier to turn into reserves, right? But what's going to be the environmental cost? That's what we're looking at here. All right, if we jump back to our workbook, okay, we're looking at, I'm asking you about how long does most CO2 stay in the tub? Find that out in your textbook, it says. And then explain 2 ways that CO2 can leave the tub, okay? And I've talked about that already. You guys get to tell us a little more. And now here we have, what does it mean that our fossil fuel resources are greater than our reserves, right? Here's the resources, here's the reserves. That was what I was just explaining to you. All right, so go reread that in the book, listen to what I just explained, and let us know what you understood. All right, so that's 20.1. Here's our last one, is 20.3. So let's go take a look at our book. All right, so here's 20.3. I'm going to open it up, and we're talking about abatement. So some of us might have heard of that term abatement before. And basically, abatement, if I click on this, it's a policy designed to reduce environmental damages. Okay, so abatement is all about reduction. And it's reduction done through policy. So if you remember when we were looking at the last chapter, and we're talking about remedies, right? Different ways that we can fix or prevent market failures, right? And we had the idea of taxes and quotas and bargaining and ownership, okay? Those are all types of policy. Those remedies are policies, okay? So when we're looking at abatement policy, we're looking at things that can be done to help change people's behaviors in a way that's favorable for the environment in this case, okay? So environmental damage abatement, trying to reduce that damage, okay? In order to do that, there's a couple of things. We can find technologies that are less polluting, we can consume less damaging goods, or we can ban or limit the use of harmful substances or activities, okay? That's the policies, okay? The economic cost of immediately eliminating all CO2 emissions would exceed the environmental benefits, right? So even though we know how to do it, we know what to do, you know, we still have to think about the economy and how can we balance the environment and the economy together, right? And that's always the big question, right? How much, you know, who comes first, the environment, the economy, because they are both completely related. As you have a climate-induced tornado come and destroy your factory, you know, you've just been negatively impacted by climate change, right? And that factory might have been creating a lot of CO2 waste, which led to the development of that climate change, right? And then once that factory's gone, we have a huge amount of cost associated with lost employment, lost contracts and work. And then, of course, the rebuilding of the factory is going to positively impact my GDP because now I'm investing more resources and labor into rebuilding what was just destroyed. Okay? But anyway, let's stay on target here. So we're looking at the abatement of environmental damages. Let's see what our workbook says. Okay, so here we say it's a way of lessening the environmental damage caused by CO2 emissions. And we want to name 3 different abatement policies. And I'm just going to put this down on one page so it's easier to look at. Okay. And so let's see, what are 3 different policies? We just talked about them. All right, so there we go. Technologies, consumption, and limiting activities. Okay, cool. All right, digging on down here, we have a lot of examples of how abatement policies can be adapted. Okay. We can go take a look at something called the abatement cost and feasibility set. So what we're going to be looking at in this unit is really the cost-benefit analysis of the environment and ways to help protect it. Okay, so what's the cost, the economic cost? What's the environmental benefit? Or we can look at what's the environmental cost and what's the environmental benefit or economic benefit. So they're all related together, right? The environmental cost is also going to have an economic cost. The environmental benefit hopefully will also have an economic benefit. Okay, so we're looking at how do we balance this? How do we understand this? How do we even quantify it? All right, so if we go back to our workbook, here we have a chart. All right, and we're asking about different abatement policies and possibilities. And why don't we just use all of them, right? Why don't we just throw them all in since we know what they are and solve the crisis and we're all done? Okay, so you guys get to think about that. And now we have figure 20.9. Okay, and let's go take a look at this figure in the book. So I just want to explain this to you. It's a great figure. So we go down here, and if you click on the figure, you can actually just kind of isolate it, and you can even make it bigger if you need to see it bigger. Okay, and what's great about this is the size here is showing how much. So what we're looking at is the abatement potential, okay? How much CO2 can we actually take out of the atmosphere? And then we have the abatement cost. Well, how much is it going to cost me per ton of CO2 to actually do this? Okay, and if we go back to my workbook, it says the width is the abatement potential, right? And then the height is the abatement cost, okay, per ton. So let's see what exactly this is telling us. So here, for example, we have the most expensive cost here is looking at the gas plant, right? Retrofitting a gas plant, really, really expensive. And the potential, we have a little bit of a potential there, right? It's not that thick. Here's another thing that's really expensive. To have iron and steel new buildings done with carbon sequestration systems, okay, and having coal retrofit. Again, these are big money projects. The coal retrofit looks like it's, you know, it has a little bit of a bigger abatement potential here, right? It's a thicker line. So that's kind of cool. Even though it's expensive, it's still going to be able to give us some bang for the buck. Going down here, we have things, reduced intensive agriculture conservation. That's really interesting, right? It's a little expensive, not as expensive as retrofitting those gas plants, but it has a lot of abatement potential. Okay, those gas plants don't have much potential at all. So that's kind of cool. So if we change our agricultural methods, we can be abating a lot more CO2. Here we have the high penetration wind, right? Those are those giant wind turbines, and they're kind of expensive, but they have some good potential. Look at solar's less expensive, and that has a big potential. Okay, and here we have another style solar, same thing. Okay, low penetration wind. Those are the smaller turbines that maybe you see around on private homes. They're not as gigantic, right, as those big turbines. And it looks like they're, you know, they have a huge potential and they're less expensive than the bigger systems. Look at this. Here's our plug-in cars. Okay, pretty cool. It's not a huge amount of abatement potential, but you know, there's something there and it's not so expensive. Okay, degraded forest reforestation. Okay, nice big gain there. Look at this with nuclear, and there's going to be an extra credit question with you on this because they're presenting nuclear as not being expensive and having a huge abatement potential. France, for example, has almost their entire country run on nuclear energy. But there's some cost associated with nuclear that's not in here. Okay, and I actually challenge them on their definition of nuclear as being as inexpensive as they're presenting it, because I feel that they're not taking into account the waste that comes from nuclear and the cost of managing that waste. And I feel like they're not taking into account the cost of the extraction and preparation of the fuel for the nuclear. I feel like here they're just looking at the cost of running the generator. Okay, so that's going to be an extra credit for you guys. But it's interesting to look at. Some of the other ones that are really thick, right? Here we have pasture land afforestation. Okay, so what that means is turning pasture land into forests, returning it back to being a forest. Okay, degraded land restoration, second generation biofuels, building efficiency, grassland management. So look at these real low-lying fruit, right? Hardly cost anything, and they have really thick lines. They have a lot of potential, and it's cheap. You know, it's just kind of changing our mindset of how we're looking at land and how we're understanding what it's being used for. Here's slash and burn, you know, super easy. Just cut that out, and boom, you have a lot more abatement going on right there. Okay, so thinking about what do we need to do to help people better manage their grasslands, better manage their forests, okay, that in itself has a huge amount of potential at making that drain in that bathtub a little bit wider, okay? So that's what I love about this chart. It gives us so many possibilities and so many different ways to think about what's happening out there, okay? And here this explains a lot more about it. talking about the science behind it, the different costs, you know, to set things up, right? Rapid reductions in costs. You know, how do you play one solution off of another? Okay. And when we start looking at this, we have something called the marginal cost curve for abatement, right? And that's what we want to think about is, yeah, it'd be great to say, oh yeah, let's all do solar and let's do some wind. And, you know, but is that the most cost-effective solution? Okay, so when we go down and we look at these kinds of curves, we can start seeing what is the cost of the abatement, okay? The billions of euros per ton abated, okay? Plus the gigatons abated, okay, over the environmental quality, okay, the amount that's abated. So if we take a look at this and start putting it into a curve, all right, our marginal abatement costs, now we can start seeing again where the different solutions fall on this curve. And what we have here in the inside is the feasibility set, right? These are all of the things that could make sense. Okay, if you remember back when we were looking at feasibility sets, we were looking at if something's outside of the set, then that means there's another solution that's going to be better, okay? Better and cheaper, okay? So here, or maybe there's something that's just not available, right? It's just not feasible. Like I would love to have, you know, a high environmental quality at a low cost, right here where my little finger is, but that just doesn't exist, right? I can have my high environmental quality, but it's going to cost me a ton of money. Okay, so this is what we're looking at, our feasibility set. And let's say I'm a government and I want to pay a moderate amount of money to help improve my CO2 sequestration, right? Maybe I'm going to be here. So if I'm going to put myself here, then all of the different options that might work for me could be the solar and the low wind and the nuclear and efficiency building, right? And all of those things are fall into my feasibility set, okay? And here we have some more information about what that all means, okay, with some specific examples, okay? Here we see, for example, how it is working, okay? And we're always looking for the most efficient response, the one that's going to give us the greatest abatement, right, at the same cost. So if we take a look at our workbook, okay, so here I'm asking you about this particular chart, asking you about wind and solar, asking you that bonus question about the nuclear energy. Okay, and now we're looking at this one. How do we know which solution is the best to use, and how would we use that probability curve? Okay, and we just saw that in the book, right? So some of your answer is going to be talking about what just happened here. Okay, and then the last question that I have for you guys in the workbook, and this part I was going to give you guys a break from because this goes into a little bit more detail, and because we're not together with the blackboard and everything, it's hard to kind of explain this. But look at it. It's basically explaining how the feasibility sets work. Again, looking at the trade-offs of consumption, you know, versus the environmental benefits. Okay. And we have a formula, but I'm giving you guys a break from all of that. Basically, what I want you to understand is that not every solution is equal, and there's trade-offs that we have to think of as we're going from one solution to the next. Okay, so I'm just going to squeeze through, and then we're done. Okay, so don't get too stressed out by not understanding these, because these are a little bit more advanced. We're not hitting them. But I just want you to understand the concept, right? The concept of choices, okay? And economically, what are we thinking of when we're making these choices? Okay, and here we have, you are the governor of Vermont. What solutions would you choose to implement for your state and why? Cool? So that's it. Enjoy and have a great time working on this, and I will talk to you soon. Bye.